to Einstein's theory of general relativity, space and time are combined as one unit, where time is the fourth dimension of the three-dimensional space. To simplify this four-dimensional construct of space-time, we can reduce to a two-dimensional analogy of a thin rubber sheet. Mass warps space-time around it, and this curvature of space-time affects the way mass moves. This reciprocal nature between mass and space-time is one of the key pillars of general relativity, the best theory that we have to explain gravity. More massive bodies, such as neutron stars, black holes, and quasars, will bend space-time more.
In this theory of general relativity, Einstein also proposed equations for what he coined as gravitational waves. Gravitational waves are ripples of the space-time fabric and are emitted at the speed of light when masses accelerate. Hence, aside from the physical warpage of space-time, gravitational waves can also momentarily shrink and stretch space-time as they pass.
Although the acceleration of any mass, such as humans walking around in a circle, a car revving up after a stoplight, or a rocket shooting up from the Earth's surface, can emit gravitational waves, these waves are nearly negligible for relatively small masses. Black holes, however, are massive enough to produce measurable gravitational waves on Earth should they accelerate. This acceleration is particularly pronounced in a binary system of black holes, where two massive black holes are orbiting around each other. As this binary system of black holes orbit, they lose mass and energy, increasing their orbital speed. They orbit faster and faster until a grand merger occurs, unifying the two counterparts into one colossal behemoth of a singularity. Since the orbital period increases during the binary system orbit and up until the merger, we can measure this through a chirp signal, where the period of the orbit gets smaller and smaller until there is no orbit and we are left with one black hole. This unique scenario of a binary black hole system merger can emit gravitational waves, as the bodies accelerate around each other until they merge. These gravitational waves are strong enough to be measured on Earth with highly sensitive instruments.
In fact, the LIGO Observatory, located at Washington and Louisiana, has built an interferometer that is capable of detecting measurements down to 10 to the negative 18th meters. That's 1,000 times smaller than the diameter of a nucleus. According to Einstein's calculations, gravitational waves should stretch space-time in one direction and shrink space-time in the perpendicular direction. To model this, LIGO built an L-shaped beam, where two 4-kilometer-long arms are perpendicular and make a 90-degree angle with each other. As the gravitational wave passes through, it will stretch one of the arms, increasing the length of the arm ever so slightly, while simultaneously shrinking the other arm, decreasing its length. To measure this shrinkage/stretching, there is a laser beam that splits the laser so that it travels across the two different arms. Since the laser travels a slightly longer distance in the stretched arm, it will take more time for the light to travel back compared to the light that is traveling from the shrunk arm. As the light from the laser travels across the arm and returns back to the original site, the inference is noted. If there were no gravitational waves passing through the machine, then the light would travel the same distance in both arms and return at the same point. When this happens, there is a destructive inference, where the two waves are perfectly out of phase with one another and cancel each other out, resulting in no signal. However, if a gravitational wave does pass through, then because of the distance the beams change, the distance and time it takes for the light to travel also changes, such that when the light beam return back to the original site, the wave patterns do not match up perfectly with one another. Instead, they are slightly out of phase since one of the light beams is lagging behind the other, and you get a dim light ray, indicating that a gravitational wave did pass through the interferometer. Due to LIGO having two locations, when both stations confirm the gravitational wave through their independent interferometers, we can be confident that a gravitational wave did pass through.
From this precise technology, scientists discovered the first gravitational waves in 2016, validating Einstein's theory. But in reality, these results mean so much more beyond the confirmation of gravitational waves. Gravitational waves have expanded our black hole discovery, especially massive black holes, which are the result of mergers. LIGO has detected merged black holes over 80 solar masses and have discovered 10 stellar black hole mergers, and has even detected the merging of a neutron star. In doing so, this technology has vastly contributed to our search for black holes, and in our quest to discover the 1 to 10 million stellar black holes, we've discovered only 40 with various methods, one of which includes gravitational waves. Why are we still missing so many? That's a video for another time. Channel Mag, signing out. See you next week for an explanation of black hole discovery methods.